Hi, we're going to start in 30 seconds, so if you could please settle down. Thank you. Well, welcome to the Physics Department Colloquium. This is a slightly larger audience than we're usually accustomed to. My name is Clifford Johnson, and with Michel H this fall, I help organize the colloquium. Now, the colloquium, in case you don't know, is an event where weekly we come together to discuss, hear about news, other things of interest to to physics, whether it be research or related topics. And it's usually presented in broad terms, so everybody in our community can participate. So actually, this fall calendar has several of our own faculty talking about various aspects of their research, including 3 assistant professors who are going up for tenure. They've been telling us about the sort of work they've been doing. But today we have 2 more of our colleagues who are going to tell us about some of their exciting work. And you may have heard that some of that work has been awarded in something that was announced last week. So of course, you know what I'm talking about. We're actually going to have a celebration for that after this. So this is our regular colloquium, which is a little larger, but will be done in the same way we usually run our colloquia. So we'll hear from them about the who, what, and why of the prize. In fact, we do this every year, whether the prize is local or not. It's a great way of refreshing a topic we can find out about what's going on in the world of physics. So briefly then, I will give their biographies. First, in alphabetical order, Michel Devoret got his PhD in 1982 at Orsay, University of Paris in France. And he did postdoctoral research at UC Berkeley in John Clarke's group, that you'll hear about more of that later. And then he returned to France, where he was actually head of the Quantronics group at Saclay. Now, Quantronics is one of the many superconducting quantum computer architectures that Michel has led research and development of. And then in 2002, he moved to Yale's physics department. And then just last year, he moved to Santa Barbara's physics department. And he's also chief scientist of quantum hardware at Google AI. John Martinis did his PhD in 1985 at UC Berkeley in that same lab, about which we'll hear more. And his postdoctoral research was at Saclay in France. And then he was a staff scientist at NIST, the National Institutes for Standards and Technology in Boulder, until 2004. And then he moved to UC Santa Barbara physics. And then he was actually involved in the pioneering work developing a superconducting quantum computer at Google Quantum AI as a chief scientist there. He then founded the startup group Quolab, which now does sort of commercial development of some of those architectures. Of course, for both of our speakers, this Nobel Prize is just the latest of many prizes and awards that they've received. I'm not going to list them all. I think it'd be more interesting to hear from them than to hear from me. So at this point, I'm going to stop talking and invite you to invite our speakers to the stage. Yeah.
Well, first of all, I must say I've never seen such a big audience. Thank you very much to all of you to come to this event. I feel extremely honored. This is a great thing, but I want immediately to say that this has not been this wouldn't have been possible if it had been for the work of many people that have worked on quantum superconducting circuit. Between the experiments we did both John and I at Berkeley, and the field as it is today. So I would like to take the opportunity of speaking in front of you to thank all the people that over 40 years in many laboratories all over the world have worked on this field and make it what we know today, which is a field that has a good chance in making the first really fault-tolerant quantum computer. John, what do you think? Yeah.
This is a real pleasure, and thank you for so many people coming out. Moving to Santa Barbara, UC Santa Barbara was really great. I enjoyed teaching. I enjoyed all the mentoring I could do for graduate students, and it's just a wonderful place to live. I want to say I'm really looking forward to this kind of interaction today, and I hope you get to see a little bit kind of the magic it was when we were working on the experiment in Burge Hall doing this with the discussions. Because, I think we think a little bit differently, but we want to get the physics right. And I think we have lots of discussions on how to do this right and do this experiment right, how to write the papers, how to describe it. And it's a real pleasure. And Michel and John Clarke and I have been email exchanging on how we're going to do our lectures in the Nobel Prize ceremony. And it really reminded me how fun it was to work with them to do that. The other thing I want to say is, I was just, the lowly graduate student, although no one ever treated me that way. But it was really wonderful to be mentored by both John Clarke and Michel. And, a lot of you may know Michel, but I got to talk to him every day for, 2 years. And of course, John Clarke, working in his lab was great. But that really started me off on my career as a physicist in a really great way. With a good experiment, how to do it right, how to join pieces of metal in a dilution refrigerator, you name it. We talked about it. And that made a big difference in my career and really changed everything for me. So yeah. Next, what should we do next, Michel? This is.
Yes.
Did you want me to talk about what a macroscopic variable is?
I want. Yes, we're going to do this, but I want first to tell you that what was amazing in this experiment and the great discussions we had together with you, John and John Clarke. There's
something wrong with your.
Is it?
I think I'm okay now.
Maybe this one is not working.
We can speak. We can just work. Let's get into the.
Yes. Is this mic working? No. No. This is. Is it? Yours is working.
I don't think it's working.
No. I think.
We're on?
Yeah, sure you're on.
Yeah, he's on.
All right. Okay.
We never had these kind of problems in the lab. Everything always worked perfectly. But
Yes. Yes. So. Well, let's continue.
Does it work? Yeah. Does the microphone work at all?
Does it work?
No.
No. Well, you may wonder why. We are building a quantum computer when we have already problems with microphone. So before we go on and explain to you what is macroscopic quantum tunneling and what did we do in this experiment, I want to say something that was absolutely wonderful in this experiment with John Martinis and John Clarke. No matter how the experiment would turn out, whether we would prove quantum mechanics right or wrong, anyways, it was a successful experiment. I think not everyone has this privilege of doing an experiment that whatever the outcome, it's going to be a great experiment.
And what I liked from the very beginning, we all decided we wanted to do an experiment where it would definitively show it one way or the other, to measure parameters, look at the quantum phenomenon in a way that would be very clear. Because there had been some results prior to that, but it just wasn't conclusive at all. And I think what we found is by doing the experiment carefully and measuring the parameters, we exposed physics, specifically energy levels, which is the basis of quantum computation now, and we laid some groundwork for doing that.
Yes. Yes, so what was, as John said, the experiment was not new in the sense that people had attempted to see these effects before. But ours was the first experiment where all the parameters entering in the theory were measured in situ, so that we could fit the experimental result with no adjustable parameter. But yes, so I think in retrospect, after the experiment, soon after the experiment, what was clear was that we had made the first artificial atoms, atoms that don't exist in the natural world, but are just as useful as atoms, real natural atoms, to do atomic physics. It was, I remember, John, we started to talk about atoms with wires, atoms on which you could put wires. Which are great to couple different atoms, which is difficult to do in atomic physics.
And I also thought, I went to do a postdoc in Berkeley, but I was really thrilled that the group, your group with other physicists in Berkeley, decided that this was an exciting field. They were going to set up a whole lab for doing this, focus on it. This is probably the first lab that was set up explicitly to do this. And they did many, many beautiful experiments. I got to, be there in the beginning. But then other people got involved in doing this, looking at the physics. Physics was pretty clean, so that, there was a whole wide variety of experiments people could do and do it beautifully and do it well, and really start understanding all the detailed physics and in what was going on in these systems. And then, quantum computation came along in late 90s, and then, we all, saw this as a, fantastic kind of series of physics experiments, technology advancements. So Clay got involved, I got involved, many other people around the world, and it just exploded. And what I would say is, when I look at the field now, it's really exciting that there are, more than 1,000 physicists who are trying to work on quantum computation, build a quantum computer, and I'm really happy that, this work led to lots of high-paying physics jobs of doing beautiful quantum mechanics physics, right? And really trying to understand this very well, very deeply. I mean, in some sense, that's the biggest reward I see. Yes. Is, creating all this opportunity for physicists.
Yes, yes, but so I think it's also interesting for young students to hear that at the beginning, the idea that Tony Leggett was to test quantum mechanics was met with extremely strong criticism and skepticism. It was not the kind of thing you should be doing. Alain Aspect famously says that when he went to see Bell and proposed to Bell that he would test these famous Bell's inequalities that would settle the debate between Bohr and Einstein, the first thing Bell asked Alain Aspect was, do you have a permanent position? Because if you don't, this is a very dangerous field. You may become rapidly an outcast. So Tony Leggett, who was already famous for explaining superfluid helium-3, could afford to work on this weird subject of testing the boundary of quantum mechanics in the direction of microscopic variable. But you know, it was met with
and I suppose
contempt.
We were young enough to not worry about, you know, any of this stuff, and we just wanted to do a good experiment.
I had already a permanent position.
Oh, okay. And I was a graduate student, so there was no. Yeah, that's great. Yeah, I like that.
Yeah.
Shall we?
Yes.
Shall we change a little bit?
Yes. Let's change.
I wanted to tell a small story. When we were starting to think about working on this, and I think this was just about the time you came. But I was trying to get a dilution refrigerator together, you know, in order to do this experiment. And something got donated to us from another group. And, you know, I was trying to work on that. And I don't know how to describe this dilution refrigerator, especially if you look at now, but I'll say it was very sad, okay, which you agree, okay. So Michel came and he had worked with cryogenics and dilution refrigerator on your military service.
Yes, I had worked on with dilution refrigerators for my own thesis, but I really learned the trade during military service.
Did you have to do push-ups during your military?
I did.
Okay,
I was.
okay,
the first part of this military service was done in the French Marines.
Okay.
Because it was going to be only 1 month, I made sure we would really see the real military.
Okay, sorry for the diversion. I just wanted to ask.
But anyway, yes, this work, which was not very far from my lab, it was just a few miles away. But I had not, you know, it was forbidden to go back to my thesis work. Taught me a lot on dilution refrigerator.
So Michel came in and looked at this with me, and he said, I think the fastest way for us to do this experiment is to get a hacksaw and cut it in two. Because, you know, he saw this and it was just not worth trying to repair and fix and find all the leaks and whatever. And that was the moment where, I was wondering about this new guy coming in, but I thought, I think this is going to work out, you know. This is really great. And what's nice is, you know, Michel designed and built a dilution refrigerator. I was doing a bunch of other stuff. But that experience meant that in my, further career, I was kind of fearless to build these things. And, I asked you and the Seclé people, but I went on to build a bunch of cryostats, for putting, X-ray detectors on the scanning electron microscope. And we built a modern dilution refrigerator design at NIST and the like. And that really spurred me on to be fearless about making these things, and that made a big impression on my career.
Yeah, it was your refrigerator was still in the room that
we're
really? Going to renovate.
But you're not using it. No. That's old. Do you want to?
Yes. So we are going to show you a few slides.
Okay.
We will change computers, but I think it doesn't matter. We're not on a tight schedule.
We're doing an analog switching of the computers because we couldn't get the digital thing to work. But that's very, fitting for a 1985 experiment. Should I show mine first on the macro?
Yep.
Okay, great. You can talk if while I'm setting up if you want.
Yes. So we are. So let's. The first thing we.
Take
yes. Oh yes. Very good. Yes. The first thing we have to explain. So the question the experiment was trying to answer was the following: do macroscopic variables obey quantum mechanics? Oh.
So sorry.
Yes. Thank you. Yes. The question that our experiment was trying to answer was, do macroscopic variables obey quantum mechanics? And we have to explain all the words here, variables, macroscopic, quantum. And you want to start?
Yeah, I'll talk about that.
Yes.
So I want you to look at this question. And that was the first sentence in one of our papers, I think on the energy levels. And I remember I had gone to France, to Paris, to visit the lab. It was kind of an interview. You were trying to recruit me for the postdoc, but we were working on the paper. And it's like we went out to dinner and we have like a 1 hour discussion on what should the first sentence be. This is very Michel in me, because it's just totally. And we talked about it, and would we be bold enough to start our paper with a question? And I think in the end, as I remember, it's like, well, our job as scientists is to ask questions. And it's great if you can do an experiment where it's a really simple sentence about what you're trying to do in that. So I remember that as a very special time, and how important it is for scientists to ask good questions and be clear about the question. Now I want to talk a little bit about the top, why we would do this. And this is kind of brought on by Tony Leggett. The Schrödinger cat paradox is this idea as the idea Tony Leggett had is the Schrödinger cat collapses from a superposition of dead and alive, maybe, to the classical states because quantum mechanics is not allowed on the macroscopic level. It's fundamentally not allowed. And that could be one way to describe the measurement. Now, I think you and I have different views of how it happens now, but back in the time, that's what we wanted to really test. And the question is, well, what kind of macroscopic variables would you test this on? So I want to note first is that quantum mechanics, microscopic quantum mechanics, the quantum mechanics of atoms can be observable on the macroscopic scale. Okay, and the example, people talk about superconductors, but the easiest example is a crystal. And what happens is, of course, all the individual atoms connect to their neighbors, but they connect in a certain way because of the way the orbitals and everything works. But then that microscopic connection is kind of just added on atom by atom, so that in the end you get these big crystal facets. And those facets actually tell you what the crystalline structure is. So it's microscopic and exhibited on the macroscopic. Now I want to note, this is very important, this is really kind of magical that you can see microscopic phenomenon on a macro scale. And of course, a lot of industry in California is centered around the healing powers of crystals. And you see that, there's actually something to that in the sense that it's magic. You're seeing, quantum mechanics from the microscopic scale being exhibited in that way. So it is very mystical, but okay, we all understand where it comes from. Now what we wanted to do, and same thing with superconductors, the Cooper pairs cause some order parameter to, go over a long distance. Same principle though. But the idea here is, will a macroscopic object show quantum mechanics? And an example of that from the Zeilinger, very beautiful, these of a carbon buckyball structure with a lot of atoms, and then they put it through a double slit and they see interference effects. And this is maybe 60, 80 atoms, but you want to know if it's truly on a macroscopic level. So what we're doing in our experiments is to look at the currents and voltages of a wire. The currents is with millions, billions of electrons, and can you see quantum mechanics behavior out of that? And because the frequencies are high, other parameters are good, you can actually see that's going on.
Yes, so it was important, and this is what's done really beautifully by Leggett. he was distinguishing the manifestations on a macroscopic scale of microscopic quantum mechanics. He was distinguishing this from the quantum mechanics of a macroscopic variable, which in our case was a current, a collective variable in which all the atoms of the circuit are involved.
So what's nice in the end, since this works, you write down, let's say, the classical equation of the motions, which comes from the Josephson effect in E and M, and then you turn that into a Hamiltonian, and then you just turn the crank of quantum mechanics in the normal way, and then you can predict what the quantum physics is. And you just treat this current and voltage and typical variables in the normal way, and then everything works in that way.
Yes.
So it's kind of amazing. I say it's amazing that quantum mechanics works kind of at all scales. It's not physics of the microscopic only. It can be physics that you can see in many other systems.
Yes, by the way, the Schrödinger-Cat paradox is a paradox precisely because quantum mechanics is supposed to be universal. It's a universal law of every variable, whether it is the position of an electron or any variable like the collective motions of an Avogadro number of electrons. It's supposed to act in the same way on all scales. And then this is how this Schrödinger-Cat paradox happens, because, even though there should be superpositions of states, we never observe them. There is in quantum mechanics a principle, so if you have two possible outcomes for an experiment, you see one or the other. You never see any superposition or any mixture. So this is the fundamental problem of quantum mechanics. There is a sort of inner contradiction in this theory. It should work on all scales, but we know when we do a measurement, these superpositions do not happen at the macroscopic scale. So there are different ways out of this conundrum, but Tony Leggett, who's a realist and who would not let himself impressed by theories like, for instance, the many-world interpretation, we can talk about this at the end. He has this joke that people who believe in the multi-world interpretation of quantum mechanics should play the quantum roulette, because there will be always a universe in which they will be still alive, so they don't risk anything. So Tony was a realist, and for him, showing that on some scale, quantum mechanics will fail, and he chose these currents and voltages because the technology of the day was able to do that. He thought that if we would find a way that in a direction in which quantum mechanics would fail, that would solve this measurement problem, that would solve all the unease we have with the Schrödinger-Cat paradox.
And what I would say is one of the pleasures of working in this field is quantum information, is people have tried to understand the resolution of this paradox. Now, not everyone will believe, what I think, but if you look at the book Exploring the Quantum by Hiroshi and Ramon, they talk about, a two-level system connected to a resonator bath, and kind of goes through the math and talks how connecting to the resonator bath makes the qubit kind of exponentially sensitive, and then, in essence, measures it and resolves that. Not everyone believes that, but for me, that's a very practical way to understand that. And there's a different kind of macroscopic kind of doing with the decoherence that seems, or at least for me, seems to be the answer to this.
Yes, but many people think that this doesn't resolve the problem of choice, that in any given experiment, one of several alternatives is chosen. That remains a mystery. And I was really happy this summer to attend the conference. This was the Helgoland conference, which was organized to celebrate the 100th year of quantum mechanics, the 100th anniversary. And for the first time, I saw people in plenary sessions say that quantum mechanics was incomplete. This was the kind of thing you would discuss in front of a beer in a cafe outside the conference, but no one would dare saying something like this. When we were learning quantum mechanics, it was really like a revealed truth. You would learn this as something that would descended from above, and there was no way you should question that. This is why also what Leggett was doing was so outlandish.
So for our hike this weekend, I know what we're going to talk about for 2 hours. Okay, this is great. I'm glad. I did want to mention one thing before we move on. You do your thesis experiment, and you're so fond of it, you always kind of want to repeat it in some way later on in your career. So I had the unique opportunity at the Google Quantum to do this bonus macroscopic, where we did, you could kind of think of it as macroscopic quantum computation, where we did a computation on a Hilbert space with 53 qubits, which is 10 to the 16 computation space, and showed that quantum mechanics still work. I mean, it wasn't perfect. These qubits aren't perfect, but it did work properly on that kind of macroscopic space. So you have some more to go here in terms of.
But you know what David Wineland says? He says that, yes, but you have to do this to metrological precision.
Do you want to talk about the experiment next?
Yes. Do you have other slides?
I'll put up my slide. Is that going to be good for you?
We can.
Can you wing it?
Yes. Okay.
Well, we can at least explain the experiment.
Yeah. But maybe so.
Do you want me to point to it? I can be like them.
Yes. Let's discuss maybe the principle of the experiment. So you have on the left, you have actually the way the experiment looks like. You have in this, if you look closely here, you will see a chip. That was a chip of about a centimeter by a centimeter.
Side, yeah. You can actually, if you get up close, see the wires of the chip, and the junction goes right here.
The wires are bounded by indium to the rest.
Yes, indium.
So the chip is minuscule. The whole experiment is all these cylinders that you see, and those are filters. These are copper powder filters that isolate this superconducting chip from the external noise. There's of course the noise that comes down from room temperature, and all kinds of parasitic noise from radio and TV stations. Cell phones didn't exist at that time, and things are getting much worse now. So in these cylinders, you have a wire, and it floats inside. Oh, thank you. It's yeah. So here, this is one of the cylinders, and it's filled with copper powder. You see John had a machine, this little hole here, and we were filling the cylinder from that hole, and the screws closes on. And so most of the volume of this experiment, which is actually connected to the mixing chamber of a dilution refrigerator, is this copper powder filter. Now, what was really interesting was that we thought we were inventing something interesting in these filters, a way to connect to a quantum circuit without actually having the noise going down. But in fact, we were rediscovering a military secret. So the same kind of techniques unknown to us are used in military apparatus to protect electronic equipment from the detonation of a hydrogen bomb, which sends in the atmosphere a very fast microwave pulse. So, so this we learned later when we went on to optimize at Saclay these filters. Maybe something we should note here is what you see are here, these golden parts here are connectors. These are SMA connectors. These are microwave connectors. So this was the new aspect of this experiment. The Josephson effect is an effect that you can measure with just DC equipment. But the Josephson effect is actually a very high frequency component that has oscillations in the microwave. And it was very important. This was the new aspect of this experiment. We were probing the dynamics of the Josephson junction at this very high frequency and controlling it, which was not done in previous experiments. So ours was new in the sense that we had all these control experiments at microwave frequencies to characterize the dynamics of the degrees of freedom that were supposed to be quantum mechanical. Let me stress again that these degrees of freedom are just the currents and the voltages of this chip at the macroscopic scale. So I am maybe...
Let me just say I really love to be an experimentalist. You know, at the time, things have changed so much in 40 years. But if you look at this wire right, this injects microwaves into the chip here, and this is an attenuator. But this is actually the tricky part. This is a coax line that it doesn't put much heat down to it. And you couldn't buy it back then. So we had to make our own coax. We had to make our own filters. You know, various things are custom designed. There's a lot of microwave engineering that goes in this. And we spent, well, first of all, we did an experiment without all the filters and the like. We just did it at 1 Kelvin, and it ended up miserably. You know, it didn't make sense at all. And then we started thinking about filters. We went over to the astronomy department and used their equipment to check how everything works, and ended up something like this. But as soon as we worked on the filtering and experimental design, our classical data was just like spot on, and we knew, that we could get this to work. So, all these little things here that may not seem much to you, that were very important for us.
Yes, do you remember, John, that the radio astronomers provided us a network analyzer, which at that time an institute, only a whole institute would have only one network analyzer.
And we had to read microwave books to understand, kind of what all the engineering principles were behind this. Mm-hmm. And that was key to understand. It was up until then, it was not a microwave experiment. And that was, it sounds trivial now, but that's something we had to figure out.
No, I think we have to explain what are these two set of datas. But I think that before we go on and explain what this is, because you see on this middle.
Do you want me to put on your slides?
Yes, let's put on my slides. I will explain very briefly what was the principle of the experiment.
I think you. Okay.
Yes, it needs to see. Okay, so let's see. Okay, so we talked about Tony Leggett. We talked about macroscopic variables in superconductivity. Maybe explain exactly what are these macroscopic variables, I think it is good to introduce the subject by taking the most simple electrical circuit that you could find, an LC circuit, which is here I have more or less copied what you have in your cell phone, the kind of circuit which is made by printed circuit techniques. So you have on the left a coil and on the right a parallel plate capacitor. And let's imagine that this is made of aluminum, which at the 20 millikelvin, the temperature of our dilution refrigerator, it's all in the superconducting state. So this system actually at low temperatures has only 1 degree of freedom because all the electrons are frozen and all the electrons form a fluid which is essentially incompressible, and the only thing that can happen, the only motion that can happen is that the charge slushes between one plate to the other. And we can actually compare this LC circuit with the hydrogen atom. So as you know, in a classical description of the hydrogen atom, you have the electron that goes around the nucleus. For the moment, I'm just showing classical pictures. We'll see what happens quantum mechanically. In the LC circuit, all you can do is displace bodily the electron condensate. All the electrons form an incompressible fluid, and the oscillation of the LC circuit, you see, is just this fluid, just slushes between the two metallic plates. There's an analogy. In fact, instead of having a unique electron moving around the nucleus, you have a whole macroscopic number of electrons whose center of mass plays exactly the same role as the electron. And you can draw an analogy between the two systems. The big difference, and that's also a way in which we can say that this system is macroscopic, is that the hydrogen atom has the dimension of a tenth of nanometer, so its dipole moment is only 1 electron times an angstrom. But here you have also a charge which is a few electrons, but they oscillate on a much larger scale, and the dipole moment is essentially orders and orders of magnitude larger than that of the hydrogen atom. So this is, in a sense, the way you can think of these experiments as macroscopic. These are systems with a huge, absolutely enormous dipole moments, which have, there's a good thing and a bad thing associated to this. If you want to couple two of these atoms, it's very easy. They talk to each other very well. And that's the basis of the quantum computer that John had built at Google. They really privilege this aspect that you can have extremely fast coupling between two artificial atoms, unlike what happens, for instance, in natural atoms, where the dynamics is much slower. Here you have this very strong coupling, so you can build a very, very fast machine. The problem is that, of course, these systems coupled to every other electromagnetic system, so there's a lot of potential parasitic couplings which actually correspond to decoherence. That's going to limit your control, the control of the quantumness of the system. So you have to essentially work around this. So something that Tony Leggett had not thought about was that, well, in this LC circuit, there are quantum energy levels. After all, this is an harmonic oscillator. The energy should be quantized, and there should be this ladder of states. Why didn't he propose this experiment? After all, you take this aluminum oscillator, it should have a quantized energy level. Why don't you see the levels? Well, you're out of luck, because the harmonic oscillator, if you excite it, actually you will not go from the ground state to the first excited state. You will form a superposition of all the levels. And in fact, you get a very, very classical behavior if you look at the first order response. So if you measure the charge or the flux, you will see exactly the same thing as for a classical oscillator. And in order to reveal the quantumness of this system, you would have to do something very complex, which would be measure the specific heat. But here we're talking about 1 degree of freedom. So yes, you could see the Dulong and Petit law that says that, okay, the specific heat is constant at high temperature, but should fall down exponentially near zero temperature. But this is not going to happen. You don't have the resolution. At least we didn't have the resolution. Now, this kind of experiment is doable, but not 40 years ago. It was absolutely out of the question. So this is why I think Tony didn't think about this most simple experiment. So we had to do something more complicated. So with the Josephson junction, you can have a nonlinear oscillator, because despite the fact that the junction is represented by a cross, the relationship between flux and current is sinusoidal instead of linear. So this is a great component for studying nonlinear effects. And now the levels are not, they are not equidistant. You can address each transition separately, and we will see this in a moment. Now, coming back to this experiment, how did it work? So this junction that we saw earlier, now it's blown up. There's this drawing of you see something that you would never see today. So this Josephson junction is made at the intersection of two metallic films, two metallic strips of metal. But if you look closely, it's a niobium lead junction. So now I'm going to ask John, who's working on making a better junction. Why do you think that we should not, at the moment, continue with the niobium lead junctions?
Why niobium junctions are bad?
Yes.
Because people have done 1,000 experiments.
You want to?
People have done 1,000 experiments and shown aluminum is better. Also, niobium has subgap states that aluminum doesn't have. But I can answer this in a lot of maybe different ways, but I think it's a little bit mythology in my view. You might have an actual metrology kind of explanation that I would like to understand.
No. What happened was that after we did this experiment, we became aware that these junctions didn't have that good a reputation because of the oxides of niobium.
So we never got a high Q, low loss system with niobium, and so we switched. Okay, and then the problem is niobium has these suboxides that are semiconductor or normal metal, and it's kind of a dirty material. But that's what we did at the time, and it was good enough for this experiment.
Yes,
but
and
we had to switch.
Yes, the reason why these junctions, which were not in retrospect all that good, were used in this experiment is that both lead and niobium are actually superconducting at 4 Kelvin. So you could do a lot of tests of the quality of these junctions without having to cool down to 20 millikelvin every time. So this was very precious. We did our first experiments testing the microwave, as as you mentioned.
We have to test our system. But we could test it at these high temperatures and still understand if it was working right.
Yes.
And, okay, you need lower temperatures and then you cool it down. Yeah.
So on this drawing, you see these black arrows. So these black arrows, they stand for the current we were sending to the junction. We were sending a current through the top electrode, the lead electrode, and the current was going through the tunnel oxide of the junction and into this niobium electrode. And so what was this tunneling that we observe? So this little schematic explains what happens. So on the left, this circuit, which I have drawn, so it's a schematic, of course. So you have the cross, which is the Josephson tunnel junction. The capacitance immediately to the right is the self-capacitance of the junction and all the parasitic capacitance of the external circuit. And then the measuring apparatus is modeled here by just a resistance, which we try to do the best job we could so that this was close to the reality of the experiment. And when you pass a current through a junction like this, you see a zero voltage across the junction because the state of the current, which I have drawn by this wavy red line here, when you represent the state of this current as a point on the potential of the Josephson junction, which is this blue, we were saying washboard potential at the time, but nowadays no one knows what is a washboard. So, well, this wavy potential that represents the tilt of the Josephson potential when you pass current. You see this red ball is not going to stay there forever. There is a phenomenon which is equivalent to the alpha decay of a nuclei. There's, in alpha decay, an alpha particle tunnels out of the nucleus. And here it's a bit the same thing, except that what tunnels is the state of the circuit. So when this red particle here, which is a generalized flux associated with the junction, then it rolls down the potential, and then a voltage appears here across the capacitance, and we can measure this voltage. And by timing the duration between the initial preparation of this particle here in the well and the moment it escapes, we can measure a sort of half-life of the phenomenon and measure again this half-life as a function of all the parameters we had at hand, which was, of course, temperature, but also the characteristic of the junction. And now I will let John explain the curves that you showed in...
For the energy levels?
No, we are going to, I think, we're going to show how the escape of the particle from the well varies as a function of... so I think... John, we are going to return to your slides for the moment.
You would like to return to my slides?
Yes.
Okay, that's great. And I can explain the two experiments after that background. Okay. Oh, come on.
Yep. Excellent. Sure.
Come on.
Yep. This is what we call the analog switching.
Okay. Thank you very much. So with that and very nice description,
Should it, is it?
should come on.
Oh,
There we go. Yes.
Excellent.
So the basic idea of the Joseon junction is it looks like a superconducting short when the current is less than the critical current of the junction, which is set by the material's properties. And then when it gets to the critical current, or maybe a little bit before, due to thermal fluctuations or quantum tunneling, it then turns into an open circuit, or and then you see the resistance across it. So it kind of looks like a normal metal then. So it's switching between the superconducting state and the state. So what you can do is measure, how close can you get to the critical current, and then what's the rate that it switches to this voltage state, which is either, with the potential Michel is talking about, it's either going over the top at high temperature, and this is just, the standard Boltzmann factor, Arrhenius factor. It's a temp frequency times e to the minus delta u over kT. So it's essential physics, and we check to make sure that's working right, and that's fine. And then what we do is when we look at that rate, we know the temp frequency, we know the potential, so we can pull out something we call T-escape. You fit that data to an Arrhenius plot. So when you do it at high temperatures, I put it over here, when you do it at high temperatures, it's a thermal activated process, and you expect that if you vary the temperature of the device and you measure this escape rate and turn it to a temperature, that T equals T escape. And that's what you see down to about 100 millikelvin or so. And then when you go colder and colder, you're no longer, the thermal escape rate gets very tiny, but now you can quantum tunnel. And then the escape rate gets enhanced, and then you see this leveling off here. Now this is the data that we get from the experiment, and then from knowing the parameters, we get a prediction of what that tunneling rate should be, which is within the experimental error bars, and you can kind of see what's going on. Now, one of the things we talked about is we need to do check experiments. How do we know we don't have an external noise source and something going wrong with the experiment? So what we did is we took our junction, which is right here, and then there's this can that goes off the thing here. We put a magnetic field here, which goes through the junction, and it reduces the critical current by the magnetic flux going through it. And in that case, instead of a critical being at 9.5 microamps, it's something like 1.4 microamps. And when you work through that, this is a lower frequency device, and lower frequencies mean it's looking more classical, okay? And in that case, the tunneling rate at low temperature, it starts to flatten out a little bit, but it's much lower temperature than this. So this gives us an in situ check that the temperature of the system is what we expect. And here's the crossover temperature here, and here's the crossover temperature. You see it kind of scales properly that way. So this is a really big check, that we're seeing macroscopic quantum tunneling. Now the other experiment I wanted to show you here is for energy levels. And what's interesting is if you go back to the history of quantum mechanics, one of the strange things that happened in the beginning was they would look at the excitation, let's say a plasma of a gas, and instead of seeing like a continuous spectrum, all different colors of light, which you kind of expect classically, you would see discrete frequencies that got emitted. And you can see this every night. You go out on the street under a yellow sodium lamp, you're seeing a sodium lamp. There's a distinct frequency of that. So why did these atoms just have these discrete frequencies in it? And of course, in the end, it's quantum mechanics. There's kind of standing waves of the electron around the atom, and then you can make jumps between various standing waves, and that way you see the discrete light. So what we did is we actually did the experiment where we would look for the energy levels, and what's nice about looking at the discrete energy levels is then, that's direct observation of the dynamics of what's going on here. So what happens here is, in the theory here, this is energy levels, so this is versus current, but this is what's going on. As we increase the current, okay, then what happens is at low currents, you're farther away from the critical current, you have a big barrier, okay? And then that barrier shrinks as you go to closer and closer to the critical current. But also, this kind of becomes a flatter barrier and the frequency goes down. So what we do is we put in a single frequency, but then vary the frequencies of the qubits. And what happens is at low currents here, where we can start getting the microwaves resonant with this 1, 2, 3 to 4 transition. And then a little bit higher, we're now seeing a 1 to 2 transition, and here seeing the 0 to 1. And that's what we see in the data. We see a background escape out of this system, either thermal or quantum mechanical, but then we look at the enhancement of that escape, and you see at this current we have a big peak here, which is this transition. This current right here, there's a second transition, here a third, and you note that these transitions are getting wider and wider as you expect as you get the higher energy levels, the matrix elements. It can radiate faster. So this is and then you can show from the predictions where the energy levels should be, and basically they are exactly what you expect. What I personally like about this is we had set up this new sample. You see this is 30 microamps instead of, 9. So it's a new sample. We're just tuning it up, playing around with the frequency. And then on the oscilloscope, which was kind of checking what was going on, I could see 3 dots. Okay, these three dots, these 3 transitions. And before I even analyzed the data, I knew we had a really interesting sample. Unfortunately, you weren't there at the time, but I got to, experience that, and then you plot it out. The other kind of funny thing here is I apologize for the poor quality of this figure. You see, you can barely see the dots here. I'm sure you can in the back. This is because we printed this out on a dot matrix printer. That's what we had for XY graphs at the time. And then we took that piece of paper over to the drafts person, and they, drew it all up, and and they didn't want the person to have to reproduce all those dots. So, okay, it's not too exciting of a plot, but that's what it was like back then. We were just entering kind of the digital age of doing this. So with that, should we go to the Q&A session? Is there anything else you wanted to add here?
No, I think we should go. We should go into the Q&A now.
Yeah, okay, great.
So we can,
Thank you.
So we're roving around the various aisles. Where possible, there should be people with microphones. And if you could come to where you see hands up, and let's try and move this a little bit swiftly so that we can get a few questions in before it's time to transition to the next thing.
The physics professor.
So, yes, I see, but I'm waiting for you to have a microphone, and
I have a very loud voice.
Okay.
well, it'd be nice to have it recorded. Okay, borrow mine.
John, I wanted to give you an opportunity. There's so many young people here who grew up in California, went to high school in California, have gone to the University of California, and John and I met when we were freshmen in physics classes at Berkeley. And I thought, you might want to take a moment and explain your journey to becoming a physicist, because you were always very focused. I remember, because I was very unfocused. I thought you were very focused. Most of the other people like you actually ended up like process engineers in Silicon Valley, people who knew as much as you did. But somehow you've ended up doing this, and there's got to be an interesting story. I know some of it, but I want you to be able to tell people.
I do want to say let's make sure we leave time for young people to ask questions as well. So
yes, I want. I'll make it quick.
No disrespect.
But that's a fine question. So I grew up in California. My dad was always working in the garage. I learned how to build things from him. I always liked math and science, electronics hobby in high school. But I loved my physics course in high school. Really excellent teacher, kind of can visually explain things. So when I came to the university, that's what I wanted to do, physics. And we were fortunate to take these honors physics courses from excellent professors. It was really, we took E&M from Jackson. Okay. And he snuck on some of the tests we had, some of his easy problems from his book. We didn't know at the time, but those are the ones we didn't get, by the way. And then I always loved being an experimentalist, so when I got to the senior lab, I loved that. I started doing experimental work all the time. I loved with John Clarke, he was building instrumentation, doing this new field of quantum circuits, and got into that. But I would say, I wanted to be a research scientist, but working with John and Michel was just such an inspiration for me to work with, really good physicists, see how physics was done. So it's very natural to want to kind of continue that and reproduce that. But I would say my strength, let's say, is more of instrumentation, building things, learning how to build cryostats right and electronics right. And that actually served me well. So those of you who are maybe less, better with building things or engineering, there's a real place for you in physics, and it's an important skill. And I would say, you had your own skills, John did. We were able to work together in a great way to combine all that to do this experiment.
Thank you.
Students, please.
Yes, we would love to have a question from the student.
Here.
I saw your hand up first.
This is
Thank
yours.
you.
Thank you.
Okay.
Thank you. Hello, my name is Frank, and I'm a physics freshman. And there's so many different fields of physics to explore, and I'm only at the very beginning of this journey, and I'm wondering what to look for. So could you please could you please share maybe one characteristic, one thing I should look for in all those exciting fields of physics, to choose a field to explore?
I spoke last time.
So
I can say something, but it's your turn.
Well, I will tell you what I tell graduate students that come see me and are looking, for advice on what fields they should work on. And I have to tell you my own personal story, because when I started to do physics in a professional lab in graduate school, I went to see these physicists and they were all depressed. Why? It was the beginning, it was 1971, and the funding at that time was severely cut in physics. And they said to me, well, you shouldn't do physics, you should do biology. This is the science of the future. Well, I went to biology labs. I even studied biochemistry, but it was much less fun than physics. As John says, in physics you get to work with a lot of interesting things, like that you smell oil in the machine shop, you saw down, the tactile environment is much more interesting in physics than in biology, I think. So I thought, well, this science that physics has been going on for 2,000 years, maybe it will last a little bit longer. During my PhD, let's have fun.
Let me give a little bit more optimistic thing.
It was important to have fun, and
That's true.
So I think this is really important, is to try to go to the place where you think you will have more fun. Don't think too much about strategizing. Which science has a future, which one is decadent. All these things change very rapidly. So you should try to get a good physics education first.
Yeah, and I heard at the time
that maybe people thought condensed matter physics was kind of dying out at the time because they had figured out semiconductors, superconductors, a lot of things. But if you look at what happened, is people invented these, mesoscopic or things, other things. They invented new devices and new physics to see it, and then it exploded, greatly. I think the same thing happened with AMO, atomic molecular optical physics.
The atomic physics is like the phoenix. It is rebirth always from its ashes.
So what happened in my case is that, I talked to professors, but I talked to John Clarke, and they were doing, quantum mechanics of these electrical systems, which I thought was fascinating. And, I don't know if I had the right intuition or not, but it sounded really interesting. Joined this group with the conferences. I saw what the people were talking about, and it's like, well, maybe I was naive. Well, we can do that, But I did go to John Clarke and say, I'd like to do this. And he said, well, the experiments have already been done. And, which is, you have to do something new in science. But then John, I think Michel and I, we thought about it a lot and said, well, how can we do it differently? Okay, and doing it differently and measuring all this just kind of created the field, because then you saw how to do things. And we were very lucky because this physics, experimental physics, was very clean. We were able to build a quantum computer in the end, which was not at all obvious at the time from any of the data. So you have to be, always interested, figure out what's going on, see things, and then if something really interests you, you try it. And, sometimes it works and sometimes it doesn't work. And then as you get older, you get a better sense of what's, the forefront, what you can do. And, it's also being kind of lucky to choose the right thing to work on. But you guys knew at Clay right away that this would be a big field, and they started a whole group on this.
Yes, I have to make the record straight. I have to admit that in between the beginning of my graduate studies and the end, there was the oil crisis. So all of a sudden there was much more money in physics.
Great.
Can we take one more, maybe one last? So I think we have, sadly, time only for one last question.
Too bad.
And I see a hand. Do you have anyone over there? Do you want to? Okay. I think. Okay. Scanning. Maybe. I don't know. We've no microphones. Okay. I'm gonna. I'm not sure who. Lots of hands. Okay. Here we go. Last question.
Hi, I was just wondering if, before you won the Nobel, would you have expected this work to be the part of your career that won the Nobel? Do you think that this, to you, was sort of the peak, the most exciting thing?
That's a great question.
I'm just going to say it's very bad for your mental health to expect anything like this. Okay, and let me just be very honest. Michel doesn't have my story, but I'll tell you my story. Is that, you kind of know that you're maybe, on the list, or people look at it. They have Nobel symposiums where they invite people, they give talks, and you do it. So to me, that's the ultimate reasonable goal, to get to that, because that's a small number of people. So, but when the time came around, it's like, okay, maybe I'll get woken up this morning, and then you don't, and you're kind of depressed. Okay. But then you get back to work, and it's okay, maybe for an hour or something. I don't know, that doesn't happen to you. That doesn't happen to Michel. But I do want to say that this year, I just got so busy with my company and kind of got over this a little bit, so I didn't even know what day it was, My wife didn't know either. And that's the best way to be surprised. And it's really, really, really great.
Yes. Yes, I hope I will be believed, but I was so busy with actually the moving of my lab and the people in my lab over there. moving crates from...
You have a lab set up.
Exactly.
Yeah.
So I was thinking more about the trajectory of my lab, whether it was going to get to orbit or not. I was thinking...
The sad part is we don't get to go into lab and uncrate and, build your lab. You have to put that off for a little while. But it's okay. We're okay.
Maybe on that note, we should maybe bring up the department chair to start the congratulatory phase. But let's at first end.
We were just saying, if the physics department can host another event where the students can come and ask us questions.
Awesome. Oh, sure.
That would be, we're sorry we talk so much, we're professionals.
Okay.
And let me just tell you a small story.
Let's
Go ahead.
You're going to do this story, but I'm going to pass that story into the next phase.
Okay, go ahead.
And let's thank our colloquium speakers, but in a moment we'll have a chance to congratulate them. So, you do it.
Thank you, Clifford and Chenke and Michel and John, for quickly organizing this absolutely wonderful, enjoyable colloquium. Now I want to move to a new phase, which is the reception, where we want to celebrate the achievement and the recognition of our colleagues with our colleagues. And as part of that, we've arranged refreshments outside with a forecast of a beautiful sunset, which is better than yesterday's forecast. But first, I want to thank and congratulate those involved. So I would like to thank the campus leaders whose support and vision really built the foundation for the physics department and its success. And it's really why we're here today. And I'd like to thank a few people in particular, starting with Pierre. So Pierre Wiltsius, Emeritus Professor of Physics and the former Bruce and Susan Worcester Dean of Science on campus until last year, who has supported science and physics, was key in recruiting Michel and actually quite a few of us here in the room. Thank you. Shelley Gable, who is our current Bruce and Susan Worcester Dean of Science. Thank you for your vigorous and creative support of science for the past year. And Henry Yang, our former chancellor for 31 years, thank you for your fierce advocacy for the campus over those times and for steadily supporting the department, its development to its current strength. David Marshall, our EVC and provost for more than 10 years. Thank you for wisely piloting us onward on the mission and upward through what seemed to be sort of continuous storms. And thank you for recruiting Michel and many of us here. And our new chancellor, Dennis Asanis, thank you for providing support and logistics for making this event work out. And thanks for taking on leadership of the campus into our future to maintain and to build on our strength. Thank you all. Actually, not just me, all of us. So we're pleased that you could be here today to join the colloquium and now the celebration, and we'd be interested to hear any thoughts that any of you are willing to share with us. If you want to.
Yeah. You can keep standing. You've been doing it for a while. So first of all, good afternoon. I couldn't even tell you how thrilled both myself and my wife Eleni, who is sitting here, we are to see so many of you, so many of our students, our postdocs, our faculty, obviously our staff in the physics department, which, by the way, in case you don't know, it's the #1 in the world. And all the other amazing disciplines that we have here at the University of California, Santa Barbara. I have to tell you that it has been a great honor for me when I was offered the position to succeed Chancellor Young this past summer. And, it didn't take me long to accept the offer because obviously I was aware of the amazing excellence of our terrific university, and that's what really drew me here, the amazing campus that we've built. And I truly want to thank the efforts of Chancellor Young, Henry Young, as well as his wife Dilling for so many years. Elaine and I look forward to getting to know you better and building a friendship with you. Let's give him a hand. Thank you. And also, I believe, and if I'm wrong, please tell them I mentioned them. We have some other amazing Nobel laureates here in audience. We have Professor Nobel laureate David Gross, the Nobel Prize Physics in 2004. Thank you. We have Professor and Nobel laureate Suji Nakamura. Thank you. Nobel Prize in 2014. And Professor Nobel laureate Alan Heeger. Thank you. It's the Nobel Prize in Chemistry in 2000. So we thank you all, and so many of our other Nobel laureates. I'll speak a little bit more to that, in just a minute. But I do want to also add my thanks to our previous dean and the current dean, Sally Gable, as well as Pierre Vilcius. Thank you for being here, but most importantly, I want to thank these two wonderful people here, Susan and Bruce Worcester, for your generosity and your support. Thank you so much, deep from our hearts. You've done so much for us, and we almost couldn't find seats for you. I was feeling embarrassed. Thank God our two Nobelists were standing all the time, so we didn't need those chairs. I also want to acknowledge, obviously, all the other members of the senior leadership team who are here, our provost, our vice chancellor for research, our chair of physics for your great work you're doing to nurture our wonderful department. And we also have some friends who are coming from the community, the chair of the Santa Barbara County Board of Supervisors, Laura Capps. I don't know where Laura is. But, Laura, great to have you here. Yeah? So nice to have you and your partner. And also the mayor of Carpinteria and UC Santa Barbara alumna, Natalia Alarcon. Yes, it's great to see you. Now, most importantly, now let's get a little more serious for 10 seconds. And let's offer all our hearty congratulations. Let's really give them a standing ovation to our two distinguished colleagues, Professor John Martinis and Michel Devoret. So I have to tell you a few things, how I met them. So really, I hadn't even met them till the morning of that Tuesday. So when I got a phone call, said, hey, you haven't been on the campus, not even a month or so, and you have two new Nobel laureates. And I said, I know how to pick winners, this is an amazing campus. So I didn't do really anything. I'm just your good luck charm. But I know you told me both that as a student asked, did you know you're going to get a Nobel laureate? And I get the same question, which I always feel unfair. Did you know you'd be the chancellor of UC Santa Barbara? And I tell everybody, when you grow up, it's not good for your mental health, to think you're going to do this, but do excellent work, consistently and persistently. And then the results come one day, and that's so much better. But anyway, I got the excellent news. I said, I've got to call those fellows, and I've got to get to know them, and I really want to make sure that we have a nice press conference. But, here's the hiccup. That day I had to go to San Francisco because we had the UC Chancellor's meeting with the president. So I said, can we schedule the meeting anytime, the press conference between now and 2 o'clock in the afternoon? So I was told, no, we don't know. It's highly uncertain. Keep doing what you're doing, and hopefully it'll work. I said, yes, hopefully it'll work. Well, I was really sitting in my plane. My chief of staff said, hey, it's about to start in an hour. Are you anywhere close? I said, no, I'm about to take off. So anyway, I called them both that evening. And first I started with John. And there was a little bit of a mix-up, in the phone numbers I had. So when I called, I said, it was your wife. So I said, is this the Devoret household? And said, no, but I know he won John Martinis. They've been calling all night long, and I did not wake up my husband. He needed a little time, to sleep in a little bit, and then I let him know later that he got this award, the Nobel laureate. I said, these are really interesting people. I need to get to know them more. So then, we had a great chat, and I called later Michel. So I said, Michel, I'm so sorry I had to miss the press conference. He said, oh no, don't feel bad. I also missed my press conference because I was really, really busy running some experiments, and I was coordinating with people about my move and this and that. And so I said, you're such an expert in quantum tunneling and all that, and you obviously saw the light at the end of the tunnel, and you left this small school, in the East Coast, Yale, to come here because this is the best university. And, he said, yes. And since I've got you on the phone and you mentioned my move, can I use my get out of jail card? My lab renovations are coming slowly. Will you help me do that? So, all night long I was giving calls to some people. I'm glad to say we've taken care of it. So, it's good. So, anyway, on the more serious side, I just wanted to say that the impact of your work, both of you, John, Michel, and with John Clarke, your mentor, cannot be overstated. It has been transformational. It's been amazing, revolutionary, as I said, known for over 3 decades. And you never know when you'll get the Nobel Prize, although I've seen some emails. I have to tell you that our provost shared with me an email in 2023 saying those guys might get the next Nobel Prize. So, some of us know, but, it's better not to share it more, and that's how we do well. Obviously, what you've done, it's lasting, it's transformational. The cell phone and so many other things that we use and we depend on, and it's a great device most of the time. I have to tell you, sometimes I hate it. I wish he didn't invent it, but it's always the feature to set the ringer off if you don't want it. Your impact is limitless, and obviously you're now our 7th and 8th Nobel laureates on our campus, which is fantastic. And I really hope, because I know we have so many more who are capable people here, that before too long, we're going to be to double digits, because we really deserve to be there, and I want all of us to work towards that, and I want especially the youth, the new generation, to have high aspirations, because that's what it's going to take us there. Your work is a testament to the interdisciplinary collaboration that we so much admire and love here at the UC Santa Barbara, and I think we do very, very well when we work together across silos, because team science, especially at this moment in time in our country, we need it, and so it's so important. So again, you've impacted the lives of so many, and I want to say that we join our faculty, our staff, all of us, our students, our alumni, our trustees, our regents, everybody, in celebrating your pioneering accomplishments. Congratulations. Or maybe you, David, whoever wants to go first. So thank you, and we'll see you at the reception.
Well, we all know that we have an outstanding physics department with its Nobel Prizes and all the accomplishments of the faculty, and combined with the Kavli Institute for Theoretical Physics, it's hard to imagine a better place to do physics. But what I really admire about this department is that it's always trying to figure out how it could be better. And sometimes that would get a little trying when whoever was the chair or Dean Wiltzius would come to me and say, hey, they have an idea that they want to recruit this person, or they want to, start this initiative or whatever. And I would think, like, aren't they good enough? But in fact, they're always getting better. And I can remember, of course, people explaining to me why we wanted John Martinis to have 1 foot on campus and 1 foot in industry, and why we had this great opportunity to recruit Michel Devoret. And it shows you why we have a department that knows how to build on excellence, and it makes all of us more excellent. I just wanted to very briefly acknowledge the relationship between these Nobel Prizes and the Nobel Prizes in economics this year. As you might have seen, the Nobel Prizes in economics were given for economists who explained the relationship between technological progress and innovation and sustained economic growth. Growth that raises living standards and health and the quality of life for people. And they really explained why sustained economic growth is driven by a continuous stream of technological innovations and improvements. And the Nobel Committee and the Nobel laureates made the point that although we've been in an age of radical innovation, that we can't take this for granted, that it depends on investing in science, that it depends on a partnership between universities, industry, and government. And I think that the insights that came from these economists who talked about the importance of society being open to new ideas, and also, what they described as creative destruction, is really kind of exemplified by these Nobel Prizes in physics. They really exemplify the idea that if progress follows innovation, innovation follows an investment in new ideas that is, in fact, exemplified by the university. The university is the laboratory of ideas in which the study of the past and the present, motivated by the need to understand the nature of things, creates that transmission of knowledge, that creation of knowledge and discovery that leads to innovation. I liked that slide that showed the question that was at the beginning of your important article. Science doesn't begin with an answer, it begins with a question. And we can see what those questions lead to, and it's many years of trial and error and experiment and curiosity that lead to this prize, but this work is what's going to lead to the great innovation and technical progress of the future. So thank you so much. We're greatly appreciative not only for the campus, but really for society.
So I'm Shelley Gable. I am the Dean of Mathematical Life and Physical Sciences. As probably the only social psychologist in the room today, I'm not going to even pretend to be qualified to talk about the technological advancements and the accomplishments of the work that they've done. But I want to rather focus just a few comments on the meaning behind the discovery. The first thing that I want to say is that there is value in fundamental science. Professors Martinis and Devoret weren't chasing a specific application or a product launch, not that there's anything wrong with that, but they were chasing a question: what is fundamentally true about reality? This is the essence of basic fundamental science. It begins with curiosity, it thrives on courage to pursue problems that are deep, that are complex, and least at the time, unsolvable. It's not about immediate payoff, it's about giving brilliant minds the freedom to think. And from that freedom, we get revolutions. Their work laid the foundation for what we now call the second quantum revolution, a future built on the basic principles of quantum mechanics. Every technological leap we enjoy in our world today stands on the shoulders of this kind of work. Investing in basic science is investing in the future's most unexpected miracles. This Nobel Prize also reminds us of the long game. Breakthroughs like this don't happen in a single grant cycle. They are the result of decades of quiet persistence, resilience, and institutional support. And they often come after more failures than successes. At least that's the way it is in my lab. We cannot predict where the next paradigm shift will emerge. However, we can predict that they are likely to come from a group of sharp minds collaborating together, like the mentor, the postdoc, and the graduate student team behind this Nobel Prize. That's why we must invest broadly in people, in ideas, in the infrastructure of discovery. You can't manage a breakthrough, but you can nurture the conditions that allow it to happen. And on the topic of investment, I want to take another opportunity to make a special note to thank Susan and Bruce Wooster, who are here today in the front. And we did have seats for you, by the way. They were just right over there, so we did have seats. Don't be embarrassed. But a little over 20 years ago, they endowed the Wooster Chair in Experimental Physics. In 2004, that was, and Dr. John Martinis became the inaugural chairholder, and it was a part of his recruitment here to UCSB. The chair continues to support our physicists' groundbreaking research and is currently held by another quantum materials physicist, Andrea Young. And finally, I think at this moment in particular, this award is a powerful reminder that science matters. We live in a time where, unfortunately, the value of knowledge is questioned, when the line between facts and opinions sometimes are blurred, and when long-term funding of discovery is uncertain at least. But this Nobel Prize reminds us that truth matters, curiosity still leads, that science, even if doubted, persists because it's self-correcting, it's rigorous, and it is resilient. So today, thank you for giving us this honor of your presence today, Professors Martinis and Devoret, but we also honor the spirit of discovery itself. So I please extend my deepest congratulations to you on these extraordinary accomplishments, and may your success inspire us all in this room to ask the big questions and keep believing in what I call the long game of science. And with that, I'll turn it over to Pierre Wiltsius.
Well, good afternoon, and I must say I'm both honored and humbled to be here and celebrate UCSB's two most recent Nobel Prize winners. I'm retired, so I can do whatever I want these days. And just 2 days ago, I drove through Humboldt County's redwoods, and now I feel like standing with two of these majestic giants. It started with a simple question, as you saw up here. So I had to reread that Physrev letter that was published, interestingly enough, on October 7th, 1985, to the date 40 years ago, the long game. It takes 40 years to really sink in. Simply put, Clarke, Devoret, and Martinis found that macroscopic electronic circuits exhibit quantized energy levels, as do atoms. And that's the basis of all what we are talking about today. Interestingly enough, though, the words quantum computing were not mentioned in this article. I looked for it. Nor were they probably a twinkle in the author's eyes. That came maybe half a dozen years later. It was fundamental science, pure and simple. Now let me give you some of my personal interactions with our two laureates, and starting chronologically with John Martinis, who studied at UCSB in 2004, and he ranked rapidly through the ranks of professors, and in 2014 he was promoted to the highest professional rank we have. And as part of that process, we always ask for external reference letters, and I reread some of those. And so one reviewer stated at the time, in 2014, quote, UCSB holds a chance with John Martinis to be the place of birth of the quantum computer, in 2014, 11 years ago. Another reviewer said, this work is of tremendous importance, which we have every reason to believe will become part of the history of our discipline. And it was a very easy promotion. John's involvement with the Google Quantum Lab here in Goleta, where the first quantum computer was built, was of course extremely successful. But it also had a small issue, and that was keeping John strongly connected with UCSB. Now, the faculty senate governs itself by the red binder, an arcane set of rules that made the dual affiliation with UCSB and Google tricky, but through deliberate and creative collaboration, we were able to find a workaround and kept John as a professor of our physics department, advising graduate students and postdocs until his retirement last year. Among many prizes and awards, Dr. Martinis was, as was mentioned already, the Worcester Chair in Experimental Physics, and I would like to acknowledge also Susan and Bruce Worcester for establishing this endowed chair, and as an alumni of UCSB, being steadfast supporters of the sciences. Thank you, Susan and Bruce. Now a few words about Michel Devoret, a slightly different story. In December of 2022, I met with Claudio Campagnari, who was the department chair of physics at the time, and a group of our quantum physics faculty. They brought to my attention that Michel Devoret from Yale might be interested in moving to UCSB. Looking at his accomplishments, it took me a nanosecond to realize the fabulous opportunity at hand. There were visits, we got glowing recommendation letters, and let me just share some quotes, and I quote, apart from being a great physicist and an inspiring research leader, Michel Devoret is also a renowned professor and an exceptional mentor of PhD students and postdoctoral researchers. Another quote said, and here it gets interesting, it would be a coup of the first magnitude if you were able to recruit him. He is one of the best experimentalists in the world and quite an excellent theorist as well. I beg your pardon, it would be a coup of first magnitude? Well, that was a challenge that I was ready to take on. But there was a potential fly in the ointment. Could we afford the starter package? Because as you may know, low temperature physics is expensive. I met with Michel and asked the question, what would it take to move you here? Or more crass, how expensive are you? He went through his list and I was waiting to hear, and I also need 5 dilutional refrigerators at $1 million apiece, but that shoe never dropped. The Southern California sun was shining on us, and Michel's requests were very reasonable. I couldn't do anything about the renovations of the lab. That is well beyond my pay grade. So I knew we could do this. We jumped over a few hurdles, and I would like to thank David Marshall and Chancellor Yang, and of course my colleagues in the physics department for their contributions, and the rest is history. I'm so proud to have played a small role in the enormous achievements of John Clarke, Michel Devoret, and John Martinis. A well-deserved Nobel Prize and a great time for UCSB and our physics departments. My heartfelt congratulations.
UCSB has been so great with accommodating everything. It's just fantastic.
And next we have Chancellor Yang. You can hear me from there. So actually today I was at a Caltech, and I chair this committee called the 30-meter telescope. It's a $2 billion project, so I'm working on it for 15 years now. So we were having a meeting. Then David said, there's a seminar here. I said I would come. So then I told my colleagues at the Caltech, they said, now you can announce that the party school's reputation is over because of the Nobels. So this is a very happy day for our university. We have a wonderful new chancellor, and both chancellor and Mrs. O here today, and welcome here. So glad to have you here. So honored to have you here. And also, our 3 Nobels are all here. I must acknowledge you, Shuji Nakamura, David Gross, and Alan Heeger. This university is very honored to have you. And also, I want to thank, Susan and Bruce for your endowment, which you give to John. So I just cannot be happier with you. Also, I would like to take this opportunity to acknowledge all of the physics faculty members. This is a bottom-up university, and 1,000 flowers are blooming. So all of our physics faculty, physics students, all of you made this department so great, made this university so great. I want to especially acknowledge and thank you, all of our science faculty, and in all disciplines. I can keep going on, but I think it's time to have a reception. Thank you.
Thank you. It is indeed time for the reception. I would like to do one thing before we leave, which is to have our undergraduates stand. And awesome. And our postdocs and our graduate students stand. Join them, please. You are a key part of our department. Thanks for coming today. And actually, thank you very much for the offer to talk further with them. I think the rest of our undergrads are on the other side of those 3 silicon dioxide barriers. So if you can find your way through them, the reception and refreshments are outside. Thank you again.